We know that the Moon's speed at perigee is greater than its orbital speed. This generates a centrifugal force that is greater than the Earth's gravitational pull, causing the Moon to move outward. And when it reaches the apogee, its speed is less than its orbital speed at that point, so it moves inward again. This is a very strange phenomenon. It shows that the speed of Moon around Earth slows down on the way from the perigee to the apogee, and slows down faster than the Earth's gravitational pull decreases. Thus, it reaches the apogee at a speed that is lower than its orbital speed, which causes it to be pulled back to Earth by Earth's gravitational pull. And on the way from the apogee to the perigee, it gets faster and faster. No one has yet been able to explain why this is the case. To explain this, we must first explain some basic rules of real physics. The size of a celestial body's gravitational field is as follows. When it rotates, it drives every other body within the gravitational field into motion. Specifically, in a tangential direction. As explained, every moving body has an inertial force that resists the effect of external forces in order to keep it in motion. The magnitude of this inertial force is as follows. And the maximum speed that a body accelerated by g can reach is limited as follows due to inertial resistance. In order for the speed of the body to continue to increase, there must be an accelerating force greater than the inertial force. This means that a driving force that is not greater than the inertial force of the body has no effect on the body. Conversely, when a body crosses the gravitational field of another body, it requires an inertial force greater than the gravitational field. Another very important rule of inertial force is that its actual magnitude is always equal to the magnitude of the external force acting on it. And it has a maximum value of. This means that inertia can only maintain speeds that correspond to the actual inertial forces. Any speed exceeding this threshold cannot be maintained by inertial forces and is slowed down by the gravitational field. The speed is therefore slowed down by this resistance until the value of the inertial force corresponds to that of the resistance. Let us assume that the speed of the Moon at point A as the starting point with radius r is greater than its orbital speed at this point by a speed delta v. This means that its centrifugal force is greater than the Earth's gravitational pull, so it moves outward and its speed decreases. The speed delta v is assumed to be exactly equal to the difference in orbital speed between points A and B. The distance between these 2 points is also delta r. This means that when the Moon reaches point B, its orbital speed is reduced by delta v. So when the Moon reaches point B, its actual speed is exactly equal to its orbital speed. Then its actual speed decreases from A to B. This means that when it moves outward by a distance delta r, its actual speed decreases by twice the difference in orbital speed between these 2 points. Similarly, when it moves inward, its actual speed increases by twice the difference in orbital speeds. This is the principle of speed change when orbiting a celestial body, and we call it the principle of double the difference in orbital speeds. When the Moon reaches point B, it is in a state of complete dynamic equilibrium. If it is not disturbed, it should always orbit the Earth at orbital speed. But, as the Moon moves from A to B, a radial motion is created, which also results in a radial inertial force. This force pushes the Moon further outwards. And it continues to move upward over a distance of delta r, up to point C. This phenomenon is comparable to a spring oscillation in which the pendulum moves upward beyond its neutral point. The principle of double difference of orbital velocities also applies to this movement from point B to C. Therefore, the actual velocity at point C is less than the orbital speed at point C by an orbital speed difference between points B and C. In this position, the Earth's gravitational force is greater than the centrifugal force of the Moon, so it moves inward again. And its actual speed increases by twice the difference in orbital speeds. From the principle of double the difference in orbital speeds, it can be easily deduced that the speed of the Moon at any point with radius r can be calculated as follows. This equation does not depend on the direction of motion or the position of the Moon.